Welcome everyone to today's HPL seminar. This week we'll be hearing from Dr. Derek Wolf. Derek is currently a postdoc at Vanderbilt University in Nashville, Tennessee. Prior, Derek completed his bachelor's in mechanical engineering from the University of Notre Dame and his PhD in mechanical engineering from Cleveland State University. Derek's current work at Vanderbilt focuses on the effect of adding a toe joint to a leg prosthesis, and also soldier-driven development of lift assist exosuits. Derek has also worked for 3 years as a controls engineer at Cummins Emissions Solutions. Derek's current research interests include rehabilitation engineering, rehab robotics, and rehab biomechanics. Derek specifically has a passion for stroke and spinal cord rehabilitation engineering and hopes to pursue an academic career in this field. A few fun facts about Derek are he is obsessed with the sport of broomball and he often travels to compete in tournaments. He also loves musical theater. He also very much loves his dog Mulligan, who will be excited to play Frisbee with him as soon as we're done with this seminar. So with that, I'll turn it over to Derek for his presentation, and then we'll have a question and answer period to follow. Thanks, Derek.
Thanks, Emily. I was excited to tell you all about broomball because someone in Calgary might actually know what it is. It's not very common down here in Tennessee. But yeah, I really appreciate you all having me here. I'm very excited to talk about my work the past few years and ongoing work where we're trying to restore reaching motions to people with high tetraplegia due to a spinal cord injury using functional electrical stimulation. And as Emily said, really, I am a postdoc at Vanderbilt right now, but most of the work that I'm going to discuss today was done with my advisor, Eric Shear at Cleveland State University during my PhD. And we continue to collaborate together now. And then also with our team over at the Cleveland FES Center in Cleveland, Ohio. So there's nearly 200,000 individuals in the United States with tetraplegia due to a spinal cord injury. One such individual shown here is Eric Legrand. He had a very famous accident playing football, which left him paralyzed from the neck down. And I just think he had a great quote that really sums up the quality of life for these individuals, in which he said, "The worst part is not being able to live on my own. I'm 27 and I can support myself financially, but I have no independence." And it's really that lack of independence that I think is at the core of the issues that we're trying to solve. And there's really limited solutions right now. There's this, very simple solutions such as holding a stylus in your mouth to use a phone, but obviously we would love to do better to really restore that day-to-day, independence to these individuals. So Kim Anderson, she ran a study in which she asked individuals with spinal cord injury, what are your greatest goals for functional recovery? And when they rank them, the number one goal for these individuals is to restore hand and arm function, because that's really the fundamental way that they're able to interact with the world. And so that's really what we're trying to do. We're trying to restore those arm motions by restoring reaching to these individuals. And we use functional electrical stimulation, or FES, to do so. FES, it works by it restores motion to paralyzed limbs by using electricity to activate the paralyzed muscles. So you can either apply the electric current directly to the muscles or to the nerves. And this causes muscle contraction and thus movement in the arm. And it's been really good for repetitive or on-off type functions like grasping, sit to stand, and bladder control, but really hasn't quite been well implemented in reaching motions due to the more complex nature of that. The image shown here is actually an implanted FES system, which is the one we use in this study. And so it's able to deliver the stimulation throughout to the muscles in the arm. We communicate with it via a radio frequency link in the abdomen, and our computer sends control signals that way. And then, as you can see, the wires run up through the arm through muscles in the chest and shoulder down to the elbow. And so this system actually, Bill Memberg and his colleagues at the Cleveland FES Center and Metro Health in Cleveland used this system with this woman. Now, again, this woman is paralyzed from the neck down. So all motion you are seeing is being driven by the electrical stimulation. And so they demonstrate that you can actually control reaching motions using functional electrical stimulation. In this particular case, the way they did it is they actually pre-programmed the stimulation pattern. So there's actually an engineer who sat there and said, okay, add 10% more biceps or add 10% more triceps, and try and work their way through that until they got the pattern, and then they just ran the pattern forward. And obviously that is a great proof of concept. It shows it can happen, but with day-to-day reaching motions, they're really goal directed. And so, if I want to reach out and pick up my glass of water, for example, one time it's over here on my right, one time it's over here on my left. Every reach is unique. Every reach is a new motion essentially that you need to do. So you can't do this pre-programming of motions. We really need a controller that can achieve any motion in the workspace at any given time. And so there have been many advanced controllers that have been demonstrated in healthy subjects or in simulation. But when we try and implement these controllers in individuals with spinal cord injury, it's really proven difficult and largely unsuccessful. And this is really because individuals with spinal cord injuries have these detrimental muscle characteristics due to their injury and due to being driven with FES. So when a spinal cord injury happens, muscles can have the trauma can lead to lower motor neuron damage, and then those muscles can't be activated at all. It doesn't matter if we electrically stimulate them. So we simply don't have force from that muscle. So maybe we can't achieve a motion that we otherwise could have. There's also severe weakness due to atrophy. I mean, many of these individuals are injured for years before we start stimulating their muscles, and we can build up some strength, but it's still significant in the atrophy. And then when you use electrical stimulation to activate muscles, there's much more rapid fatigue than when we naturally activate our muscles. And so these are all issues, and we won't address all these issues today in our work, but these are the types of issues that we really have to deal with. And so in our work, we think it's very critical to actually implement your control strategy in an individual who has a spinal cord injury, and not just in simulation or in healthy subjects. So there's really in my opinion, two seminal works that really did this and have really advanced the area of FES-driven reaching. And so the first of them is the Mundus project, and that's shown here. The way they did this is they actually used a locking exoskeleton. So you'll see it on his arm. There's a exoskeleton that's attached to his wheelchair. And what they do is they control one joint at a time using FES. So all movement is driven by FES, and the exoskeleton locks the other joints. So for example, when the elbow is flexing, that shoulder is locked in place and can't rotate. And so this was obviously had a lot of success. This individual is able to drink from a cup by himself. That's tremendous. But the movements are slow, a little jerky. I mean, when you go joint by joint, kind of as an unnatural type of movement. And then errors actually occurred because the shoulder would slip in the exoskeleton when they were trying to control the elbow, for example. So, and those errors just propagate down the chain. So one thing, we think needs to be improved is really need to control the arm as a whole system and actually be trying to actively control that shoulder instead of just trying to hold it in place. Because, as many of you who work with wearables or exoskeletons know, it's hard to lock a joint in place and not let any sort of slippage or rotation. So if we just control it with the electrical stimulation, we think there could be more success. And then another really tremendous work that came out, I guess, a few years ago now, but it's the BrainGate 2 project. And so again, this individual is, once again, paralyzed from the neck down. All motion that you're seeing is being controlled by electrical stimulation. And he's actually controlling the electrical stimulation with a brain control interface in his head. And, really tremendous stuff. Again, he's able to drink, but they ran into a couple issues. One, the all shoulder rotation is actually being controlled by the robot, so it's still coming from his brain, but it's not FES driven. And when they did single joint motions, such as just flexing the elbow, they had really great accuracy. But then there were some errors due to the uncontrolled dynamic coupling of the shoulder moving with the robot and the elbow. And the subject was unable to, unable to deal with that. Just a lot of cognitive load there. So, once again, I think with our two works, there's really two things we're trying to do. We want to control the entire arm and understand the dynamics of the whole arm. And then we also want to actually do this in an individual with spinal cord injury. So we have to account for those detrimental muscle characteristics that they have. And so that's our approach is actually, we have three parts. So we develop a person-specific model of the electrically stimulated arm and its response to stimulation. And then we use that model as the basis of a trajectory optimization to find feasible reaches. So again, because of those detrimental muscle effects, sometimes a reach may, you may not be able to reach this way. Maybe you have to go around, something like that. So we need to find feasible reaches. And then we used a model predictive control scheme to drive the arm along those desired trajectories. And so I'm going to use this approach sort of as the outline for the rest of the presentation. And I'll walk you through, pretty much the story of what we've done in the past couple of years and what we're still doing. And then at the end, have a bit of a discussion of, where I see the future of this work and FES reaching in general. So first up, we have to develop that person-specific model. Again, we're trying to account for those very specific characteristics of an individual, of a specific individual with spinal cord injury, because everyone is so different. So for us, we worked with this woman. You saw her in the video previously. She is 60 years old. At the time, she suffered a C1, C2 level injury due to a gunshot wound. Her wheelchair has a passive arm support. So you'll see that in all the videos, all the pictures of her, everything we have, it's totally passive. It's there just to support the arm against gravity. Her shoulder is not strong enough to do that. And also it helps create a safe, comfortable workspace that she can move her arm in and work well in. On her arm, you'll see the markers. So just again, in case you see them and need to know, those are just motion capture markers. We used OptiTrack. That's how we measured that's how we measured for our data collections, how we measure for model identification, her joint angles, everything like that. We use these rigid bodies on her arm, on her forearm, her humerus, and then there's one on her chest that her head is blocking. And then there's this robot. Again, you'll see it. You'll see it in videos. It is not providing motion. It is there to measure wrist forces, sometimes wrist location. We use it in model identification. And in control experiments later, we will actually use the robot to produce a damped environment. This is something we found really helps. And we think in the long run, that'll come, you can just build that into the arm support, which is going to be needed for any type of reaching for an individual with spinal cord injury anyway. But the damping really seemed to improve our performance and stop oscillation, which is very uncomfortable for a person. If you imagine trying to eat off a plate and your arm is oscillating, it's just not going to go well. So that's why it's there, and that's why we used it to create a damped environment. So again, I already discussed this briefly, but we used the Cleveland FES, the IST12 stimulator telemeter, and it's an implanted system. It has all the wires that run from a telemeter in your abdomen. Apologies. So the wires run up from there, go to different nerve cuffs or direct into muscle electrodes. We communicate with that via a radio frequency link that we tape to our abdomen that connects to our computer. So we send control signals, which for us are changing the pulse width of the signal that we're sending to each muscle. And so with this, we're able to stimulate 9 muscle groups in the arm. So we stimulate the triceps, the deltoids, the lats, the serratus anterior, the biceps and brachialis, the super and infraspinatus, the rhomboids, the lower and the upper pecs. And just one thing to note is, these are muscle groups. So when we, for example, when we stimulate biceps and brachialis, we get both together. We're not able to get one or the other. So these are the 9 possible inputs to our system that we can work with. So when we go to actually get a model of the subject's arm and how it is responding to stimulation, one possible method would be to do as a parametric model, but it's really difficult to identify the parameters of a model, especially of an arm, especially with an individual spinal cord injury. It's hard to excite the dynamics of the arm. You need a lot of data. It's just a difficult problem, and in some ways, maybe not. In some ways, not feasible. So we decided to go with non-parametric models, and so we use those where we map the configuration of the arm to the muscle capabilities. So if I'm in a given configuration, what sort of torques can I produce with the muscles that I have access to? And so to identify those non-parametric models, we shown here in this video. So we moved the subject's arm to configurations throughout the workspace. The robot would hold the arm static, and then it would, while the arm was static, it would be measuring the force at the wrist. So for one time period, we would stimulate no muscles, and that would sort of give us the amount of force needed to hold a position. And then one at a time, we would stimulate each of the 9 muscle groups at 100% stimulation. And so the difference between that static force needed to hold a position and the force measured when a muscle is stimulated gives us the amount of force produced by that muscle group. And we could use the kinematic Jacobian to transfer those force mappings to torque mappings. And then we did this at 27 positions throughout the workspace, and we repeated it 3 times. And we used Gaussian process regression as our non-parametric modeling method. So we used a Gaussian process regression to map the entire workspace based on our apologies. There we go. Sorry about that. I hit the button. Based on our training data. And so an example here of the force equivalent mapping for the deltoids muscle. So throughout the space. So if you follow those arrows, according to our models, those are the directions of force just in a slice of the workspace that her deltoids muscle was able to produce. And so with that, we have our person-specific model. And then we're going to use that model as part of our trajectory optimization scheme. And so I think the first question we have to ask is, why do we even need trajectory optimization? And so, the first thing we tried probably 3 years ago now, maybe even longer, was we just tried straight line reaching. So we tried a relatively simple feedback control structure. So we had our muscle models. We have the force that's needed to achieve a position. So that's our inverse arm statics. And again, our models are totally isometric and static. So we have this predicted force to achieve it. And then we have a PID controller that's going to, look at where we are, where we want to be, and it's going to try and change the amount of desired force to get there. We then use our model again to say, okay, well, if we want to produce, this much force in this direction at the hand to move in the direction we want to move, what are the muscles that we need to activate? So we're really inverting our model, and this is an overactuated system, so it becomes a real-time optimization problem. We define it as a quadratic program, and then we solve for the muscle activations that give us the desired force. And then we have what are called recruitment curves, which simply say, if I want to activate if I want to activate the bicep at 80%, what is the pulse width that I need to send to achieve that 80%? So just a mapping between the recruitment curve is a mapping between the pulse width that we're sending and the muscle activation we achieve. And so we simply invert that mapping to give us the stimulation command, and we apply it to the arm. And then the controller does that and attempts to drive the arm to its final position. And so, we had some success. This reach, shows it can work. This very simple PID control structure where everything's in force space. We're just simply trying to drive the hand to the target position. got really excited. Some things worked really well, but unfortunately, it didn't always work. And what we really found was there were parts of the workspace, specifically in the case of this one, the area out and to the right, where the subject really struggled to, or where our controller struggled to drive the subject's arm out. And so, again, it does bear repeating, because sometimes you lose sight of the fact, like, this woman is paralyzed. So the motion is, it's our controllers creating all the motion via electrical stimulation. And so if you notice, as the arm starts to go out to the right, it starts to look good. And then it seems to hit a sticking point. And the question, that we had is, why? What is happening at that sticking point? We know you can get out there, because frankly, we did it on accident once. So we know it's possible, but our controller is not able to do it. So what's going on there? And basically what we found was, we're not able to actually reach all parts, or I'm sorry, what we found was, it's those detrimental muscle characteristics of spinal cord injury, right? So we're trying to move out to the right. Our controller is asking for, let's say, 10 newtons out to the right, but our muscles can't produce that, right? So, and the reason being either muscle weakness, or we just simply don't have a muscle that produces force in that direction. And so that's why you get that sticking point where it starts to go out and it sticks, because we're asking for forces that are simply infeasible. So really, we needed a smarter control structure. So, as a sanity check, we actually did run a simulation study and said, is this a problem with our individual? Is it a problem with our controller? And what we found is, so what we did was we took our muscle model, we applied it to a very, I apologize, my dog started barking. Joys are working from home, right? So what we did was we took our muscle models and we applied it to a two joint link with, to a 2-link simulation with 3 rotations at the shoulder and 1 at the elbow. And we, just a very simple simulation. We had perfect model knowledge, perfect everything. And we said, can we go in a straight line path? And the answer is no. And simply what happens is, if you try and go in a straight line and don't plan a trajectory, you ask to go in directions that your muscles cannot produce, again, because they're too weak, or you simply don't have a muscle that pushes in that direction. And we also actually tried a more advanced controller. We said, well, what if we used a model predictive controller? And again, this is with perfect model information. And we're still not able to get out there. And we really kind of realized, okay, you can't just go straight lines. You need to plan trajectories. And so in our simulation study, we said, all right, let's plan trajectories, and let's use our perfect knowledge and show that it actually improves things. And what was interesting is it improved things for both feedback and model predictive control. We also added a feed forward plus feedback controller. But the muscle activation, the feedback controller would still have those points where it was sticking. As soon as it got, off path too far, it would hit these sticking points. And so really we started looking, and the feed forward feedback would happen too. So we started looking at model predictive control with trajectory optimization, and trying to use that and then implementing that with our individual with a spinal cord injury. So our trajectory, with that knowledge of like, hey, you need to plan trajectories, we go to our trajectory optimization scheme. So we take our muscle models that we have developed, our static muscle models, and we put them we created a dynamic arm simulation. So it's 2 links. It's 2 links. It's got 4 degrees of freedom. So there's 3 rotations at the shoulder, 1 elbow flexion. We just use rigid body dynamics, and all the parameters of this model were estimated via previous literature. And then this model uses that information from our muscle models, and it's torque driven. So we assume that the muscle torques add linearly. We've done We've done previous work to show that this is a reasonable assumption. And what's really important about this is this simulation has the exact same muscle capabilities as our model predicts that our subject with spinal cord injury has. And so this really allows us to handle, to predict what reaches are actually possible. And that includes, the way that the muscles cross multiple joints and in different configurations will produce different torques. That's all going to be built into this simulation. So we take that simulation and we use direct collocation to actually plan trajectories. So direct collocation, I'm sure many of you in this room use it. It really takes your trajectory optimization and makes it a constrained nonlinear optimization problem. And it seeks to calculate the state and input of this, the state and the input of the system across a discretized time domain. And the objective function that we minimized is shown here. And so that first term is sort of it's minimizing the muscle activations. And so that's sort of an effort minimization term. We want to do this in the easiest way we can with the least power and the least fatigue, for our individual. The second term is trying to bias it towards straighter line paths. There were some, when we originally did it with just minimizing muscle activations, we were getting paths where you'd like swing your arm around, and that works, I guess, in the simulation, but probably not the method that a person would want to actually use in real life. So we want to bias it towards straight line paths while still finding the most feasible or a feasible path. And what's really important is that the muscle activation and dynamic constraints are met during this trajectory optimization. So it takes into account the actual capabilities of the muscles. It makes sure that the path that is actually being asked to follow is feasible based on those capabilities. And then the dynamics are constrained for the to ensure that the rigid body dynamics are met, because that wouldn't make sense otherwise. So now that we have our desired trajectory for a given reach, we want to actually implement it. As I said earlier, we've done the simulations, we need to actually implement it into an individual. And we decided to use model predictive control to do that. And so this is our control scheme. We have our model predictive controller. The inputs to the model is based on our arm simulation, and then our optimized trajectory comes into that, which is also based on our arm simulation, comes into that model MPC control block as our input. The MPC controller will predict the muscle activations needed to achieve a desired reach. And again, we have the recruitment curves, which take activations to stimulation commands or pulse widths in our case, and actually applies in the arm. And we get real-time feedback back to the MPC control with updates. So the MPC controller that we use a receding horizon controller. So we took that simulation that we produced, and we linearized the simulation about the current state of the system. About the current desired state of the system, and that gave us our discretized state space system. And then the MPC controller predicts in real time the inputs that will best achieve the steps, the desired trajectory moving forward. And it does this by minimizing this objective function. So the first term is an error minimization. So how far, looking in steps ahead, what is the commands that'll minimize the error relative to our desired trajectory. And then the second term of the objective function is really minimizing effort, it's minimizing effort. And it's also really, in this case, so we actually, to add some integral action to this, we actually make it minimize the change in effort, and we slightly change our state space models to have inputs of change in activation as opposed to just activation. So the second term, kind of two things: it limits the change in activation, which creates like a smoothing type parameter, and it also is an effort sort of minimizer. So you're really trying to get the error as low as possible with reasonable effort and change. And what's really important here is that it, and why we like MPC and why we started using it, is it takes into account the muscle activation constraints in real time. That's really a big deal. That's going to keep us from getting into those sticking positions that the feedback only controllers that the feedback only controllers you ran into. So then to actually implement this with our individual, we created a quick day of model. So we have our previously found model with our Gaussian process regression model. We go to 13 configurations. We find, and that's just making sure, hey, are her muscles being stimulated in the same way? You know, there's differences in fatigue, differences in how her system couples and how much power comes through. So we kind of need to do a quick update of our models. So the way we do that, we just quickly go to 13 positions in the workspace. We keep those previous hyperparameters from our GPR model and we update our training data. And then we then the central resting location became the start of all of our reaches. So with her arm support, there's a resting location in the middle. And so that's the start of all of our reaches. And then we use our trajectory optimization to see if we could find feasible reaching motions to the training configuration. So it's really 12 possible reaches. And of those 12, we were able to find 11 feasible reaches. And important to note, it doesn't necessarily mean that the 12th reach was not possible. It simply means we did not find it. We had a time cutoff, simply trying to meet the subject's schedule. So anything ran for more than a couple minutes, we would kill it, kill the program so that we could move on and run the reaches that we were able to find. So we repeated that set 9 times. So we had 99 total reaches. And once again, I mentioned this earlier, the robot, in this case, we use it for some gravity compensation and also to create that damped workspace. But the motion that you see is being driven by her arm. And one other, I would call it an interesting issue that arises when we actually implement this is this scalar lambda here on the muscle activation, change in muscle activation. That's your tuning parameter for this MPC controller. And we unfortunately, we had to really tune that for patient comfort more than for accuracy of control. So, you know, if that's low, if that's a low number, for example, a relatively low number, the muscle activations can change rapidly. Well, that's uncomfortable for an individual. I mean, if you just think you're not in control of your arm and your muscles are just turning on and off, you know, really fast, that's not going to be comfortable. So really became a, you know, how smooth can we make it and still have decent accuracy? But I would say the smoothness of that trumped the accuracy when it came to actually the tuning. You know, so for a given, you know, this is the actual implementation of this. The X marks the desired target. We always start at that center location. So the robot brings us back to our central resting location to start every time. Each reach was 5 seconds long. There's 1 second to hold at the beginning, and then 2 seconds along with the optimized trajectory that we previously found, and then a 2-second hold at the end. So, you know, start it, hold for a second, move along a 2-second trajectory, and then hold at the final target for 2 seconds. And, you know, we'll watch a few more here, but as seen, you know, some are really good. Obviously not all. That one in particular is not great, but there's some that are really good. And I think, you know, there's some oscillation, but it's not super jerky. It's in general, we were really excited with this. And so, you know, just a representative trial that really worked well. And I think what's most exciting for me and for us in this trial is this is the reach that we struggled with straight line paths, right? This is reaching her arm out and to the right. That's where we used to hit that sticking point. We don't get that. We're getting, you know, smooth activation patterns. If you look in the table in the top right of this slide, those are the muscle activations for 3 of the muscle groups. And they're smooth. They make sense. You know, as we're moving out to the right, we need to get some triceps, some elbow extension. That makes sense. That's logical. Then the biceps has to turn on to stop it. And then you get a little oscillation because of those, you know, those two sort of fighting each other. And that, you know, shows that our MPC controller was making predictions that make sense to us, right? It's a good sanity check that things there are happening the way we expected. And, you know, if you look at the wrist position in the top left, you know, we did a decent job following our desired trajectories. We did there's some oscillation. It's not perfect, but I think the biggest key here, as I said, the big win is it doesn't get stuck. That is not an issue anymore. We've solved that. And so if we can improve our models a little bit, we can even improve this further. So just, sort of summarizing, I guess, what I just said, but this control and trajectory optimization structure, it really showed great potential for achieving FES driven reaching. The controller avoided those muscle saturation issues, and it was able to reach areas of the workspace that were previously unreachable, which again, that's the big win here. Over the 99 reaches, we had an accuracy of 8.5 centimeters. That could be improved. And we think, if we improve modeling of the arm dynamics or, some other, or the arm support, things like that, we can really improve this and help restore these reaching motions to people in the real world. And so, as I just said, moving forward, we really need to add those dynamics to the model. So our current muscle models, they're static, right? They're totally isometric models. And that's not how this works, right? We know that there's dynamics involved, both in muscle activation dynamics, how the arm support is interacting with her arm, how it's, there's an elasticity to that arm support. She's fatiguing throughout a day, how much of this, there's this complexity missing in the model. And now an important question is how much of that complexity is needed, right? Because every layer of that just makes this harder to do. It's harder to identify those dynamics. What we would like to do, I think, in our sort of next steps, and this is what we're working on now, and something I'm really excited about, is instead of these static models, have dynamic models that are still the non-parametric models. So still using, our lab is very fond of Gaussian process regression, but it could be any sort of non-parametric model. But using that, so right now the model maps the configuration of the arm to the torques produced by a muscle. But we could use a model to say, well, what's the current state of the arm and the current input of the arm? And then our model predicts the next state, right? And I think that's where we're trying to head with this, is moving away from those static muscle models to something that includes the current state of the arm, both probably in configuration space and joint velocities included in that. And then saying, well, if I'm currently here and I apply 20% bicep, 10% pecs, I have a prediction for what that next time step I'll be at with my state. And so I think that's really, that's what I'm excited for. That's where we're trying to go next, but we'll see what happens. But overall, I think there's a lot of positive here. I think the FES, I think this shows this sort of strategy has the ability to restore reaching to people with tetraplegia, and do it in the real world. And so I think there's a lot of excitement there. So I'd like to talk about where I see the future of this going, and both in this work, as I've kind of already discussed, but other areas that I think will end up playing in. And so a big one is epidural spinal stimulation. So there's a lot of, I would say there's a lot of momentum to move away from peripheral stimulation, where we're stimulating out on the arms and legs, and move into spinal stimulation. There seems to be some really good reasons to do so. I'm not an expert in this area by any means, but this paper actually just came out. It's a preprint, but it just came out, I believe, a couple weeks ago. And it's, if we epidural stimulation for stroke, it restored some voluntary motor control. And a lot of things that work for stroke end up also being beneficial in spinal cord injury. So I think there's a lot of reasons to start looking towards epidural spinal stimulation. I mean, a lot of people are already doing this, certainly not my idea or novel, but it's out there. And I think it's definitely one path that this is going to go to really get FES driven reaching in the real world. I think we need to improve the hardware. I think there's limitations right now in these implanted systems, things such as, if we're going to take these home and we don't have motion capture, how do we measure joint angles? How do we actually know the current state of the arm? And so that's really needs to be improved, and before it can really apply to real world. I think selective muscle activation is a really interesting area. How, as I said earlier, when we stimulate our muscle groups, we get biceps and brachialis together, but there's times you'd want one or the other, or some combo. And so we can be smarter about how we stimulate nerves. Some people are definitely working on this. If you send the correct type of pulse, maybe you can get more of one muscle than the other, or some combo. And so I think that's very exciting. And then I think fatigue management is a huge one. And so different ways, I think that eventually will have to be built into any sort of control scheme. So maybe in our MPC, we have a fatigue model built in there that accounts for this, or something like that. But I think fatigue management is huge. And this has already been done in many ways in lower limb FES, and it just hasn't yet been translated to reaching. There's some differences where lower limb is very cyclic. Reaching motions are not, they're very goal directed, unique every time. So it's a little harder to make predictions moving forward, because you don't have like the previous step that's supposedly, fairly symmetric and identical. But there's ways to do it. And I think this is definitely something that we need to improve on and get for if we're ever going to have FES reaching in, out of a hospital and out of the lab. And then one thing that I am very excited about, and I really believe is sort of the future, and I think it's necessary. You see the arm supports that people need anyway, is hybrid robot FES systems. And so we actually did a pilot study. We presented at WeRob. This was us. We worked with the Mahi lab at Rice. So that's Marcy O'Malley's group. And we combined their Mahi XO2 elbow robot with FES electrodes. So we were just doing elbow flexion, but the general idea is the FES would provide power. I mean, when we use exos, we have these muscles, and these muscles are actuators that are there. And if you don't use them, it's essentially wasted mass, right? Like you would never put a motor on a robot and just leave it. And so you have these muscles that can be used, and can provide power. But obviously there's these issues that we've already talked about. And so maybe the robot's there and it can provide that precision. And actually that's exactly what we found. So this top graph here, again, this is the trajectory we're trying to go on. You see the top graph, that's just FES, and it's decent. It goes up, it goes down, but it's not tracking. I don't think anyone would claim that's great tracking. But when we add the robot in, we're able to really track that desired trajectory well. And again, just elbow flexion. And we did this with healthy subjects, or with able-bodied subjects. But again, it really shows kind of the power of this combo. And I think the real exciting thing, and sorry that got cut off a bit, but with the blue here is if you do follow that path with just the exo, that's the torque we needed to command to achieve it. And so, yeah, you're going to get the same accuracy, right? A robot is very good. We're very good at tracking a flexion curve, but when we add the power from the FES, the robot provides much less power. So you need smaller batteries, smaller motors, like everything can get better, and you get the best of both worlds. And then I think additionally in the future, what's really exciting to me is if we can use these hybrid systems, you can use the robot to measure the state of the system in real time. You can also help measure fatigue, right? If your torque commands are increasing because your muscles aren't producing the torques you think they should be, that's immediate information that can go back to sort of update your model, be a fatigue model or whatever. And this has actually been done. They've done this in lower limb FES, walking and cycling. And I think it's coming, and I think we will definitely be adding it to upper limb soon. And I hope so. And I kind of look forward to being part of that. It's really exciting stuff. And so just, this is the final slide. I think FES really does have the potential to restore this reaching to individuals with tetraplegia in the real world. I think we need to continue working with them directly. We need to continue accounting for their muscle capabilities, their unique muscle capabilities, and keep working forward towards that independence that they so want and deserve. So thank you for your time.
Thanks, Derek. That was great. Excellent. At this time, Derek, if you're willing to stop sharing your screen, I'll kindly ask the audience members that if you're comfortable to please turn on your Zoom camera to allow for better discussion. To ask a question, you can use the raise hand function under reactions, or you can type your question in the chat box and I will read it aloud. So Derek, actually, I'll start with a question. Can you talk more about the time to complete the task during your studies? Was the time to complete the reach constrained, or was it just variable based on whatever muscle torques could be produced?
Yeah, that's a great question. We did pick a time, so we constrained the time to a 2-second reach. That was a bit of an arbitrary choice. It was sort of trying to balance what we felt was a reasonable time. I mean, obviously that's not a super fast reach, but we wanted it to be controlled, and not, especially with our early prototypes of this controller, we didn't want to try and do anything too dynamic. And so it was constrained, and yeah, we just kind of picked 2 seconds as a bit of an arbitrary, with a lot of thought, but not, just trying not to be super dynamic where we think we would introduce other problems.
That's great. I really liked your final slide where you were pointing towards the combination of exos and FES and how that can reduce the magnitude of forces required by the exo. Do you think the combination at all could improve the time to complete the reach?
Absolutely. I think all of the issues, or not all of the issues, but I think a lot of the issues of FES alone can be solved with a hybrid system. I think you can, you sort of can let the exo handle let's call it the uncontrolled dynamics, right? That when we try and do something really fast, there's this coupling or things so a big problem, I'm sorry, I'm struggling to think this through, but the big problem we have is our FES system stimulates at 13 hertz. So that is as fast as we can control as we can change our control inputs is 13 hertz, which is pretty slow if you're doing something super fast. Whereas a lot of robots, let's call it 500 hertz, whatever, you can go a lot faster in your control loops and make changes. So we can do something much more dynamic where the robot can handle the issues and the instability maybe produced by your delay and your input commands from your FES. It can handle that, so you can, I think, shorten your time frame and do faster, shorter time frame motions.
That's great. I think that's a really good perspective on how to draw on the advantages of both of the systems.
Yeah. And the 13 hertz is that can't be improved with hardware. That's inherent. That's what a good frequency to stimulate at is for an implanted system. Right? So it's sort of we can't just increase that to 500 hertz or whatever. That's just not, that there's just some rules there for safety. Always end up in the same spot, or does it matter where you start? Maybe you end up, so I think the idea is right. I think there's ways to do it. I think one thing we have noticed is, at least with the muscles we have the ability to activate, if we turn different ones on, we kind of always end up kind of stuck in the middle. So how do we get out to other places? And then there's also an issue where frankly, her tricep is so much stronger than any of her other muscles that there's kind of a weird combo where anything you stimulate with it ends up fully extended in the same point. But I think the idea is right, and I absolutely think it's a possible way to go. I don't know if that answered the question, but
sure. And I guess related to that is, I guess in some of your controllers, I'm not sure if it's all of them, you do model the dynamics of the arm, and I'm just wondering how much, do you need that? So what if you ignore the dynamics of the arm, does that make a huge difference, or is it, how critical are the dynamics?
Yeah, so in our simulation study, it mattered a lot. And so that's why we started doing it. But admittedly, that was a very simple simulation. And I think it has part to do with maybe control algorithms chosen. So it's possible if you did some sort of, an equilibrium type controller like we were just talking about, you wouldn't need them. I think the dynamics are important. I think they need to be measured essentially for a couple reasons. One is to help with the oscillation issue that we sort of discussed previously. That was a real problem. And then second, I think there's an importance of those sticking positions that I sort of talked about, where we end up in a position where we're asking for muscle activations that we can't actually get. I think there's an interesting question. If you don't include dynamics, there may not be a way through that type of state. But if you include dynamics, it's possible your arm can, dynamically move through that state, but your controller wouldn't know that unless you have dynamics built in. So that's what led us to add the dynamics and really try and model them. And that's why I would say, heading down that path on the tree of trying to even better model dynamics, is trying to account for, can we take advantage of the dynamics and to better create motions? Is it necessary? I don't know. I think there may be other ways to do it. But that's sort of why we are headed that way, is we're trying to get rid of oscillation, and we're trying to take advantage of the dynamics and our understanding of them to create more realistic real world reaches.
Well, about the oscillations, I'm curious about, so it sounds to me like you prefer to have physical damping in the exoskeleton as opposed to doing it all in software, like just using the D term. And it makes me think of, so you probably know Chris Atkinson. He's a roboticist.
A little bit, yep.
So Chris Atkinson has been working on humanoid robotics, and a thing that he likes to say is that a big thing that's missing from the humanoid robots is basically is good velocity sensing. And the problem in the robots is that you're usually sensing velocity by using a sensor that's not so great, like an optical encoder. And then you get pretty noisy velocity measurements, which makes it hard to do good stabilization. And then one of the things he's advocated for is that what the robot motors need is the equivalent of a force velocity curve, or something that is in hardware, not in software, that would help with the damping that they need. And so what you're talking about sort of reminds me of that. And I'm just wondering, can you sort of speak to using the D term in a controller versus the damping in the exoskeleton and the different advantages?
Yeah. We tried using the D term. Basically, we had two issues. One is measuring velocity in real time using motion capture. So how do we measure our joint angle velocities in real time? And then the other one, which is I think really the real issue, is with our slow control input signal. Again, that 13 hertz signal, essentially we were missing. We would be pointing in the wrong direction with our D term once we passed our point, and it actually made it less stable. So that's why we ended up doing it physically, adding damping as opposed to trying to do it with software. Is basically with our slow control signal and our noise in our control inputs and measurements, it actually made it less stable as opposed to more stable.
Great. Super interesting. It really provides a new perspective on how people have been thinking about motor control. I would say, that old school scientific stuff, how to think about it, based on what we hear about your experiences. So thanks.
Thank you.
Any other questions from the audience? Great. With that, please join me in thanking Derek for his presentation today, and thank you to all the audience members for their questions and discussion. I hope to see everyone again next week for the HPL seminar, and we'll be hearing from Tao Lee from the University of Alberta, and he'll be presenting on the design of universal talus implants. So thank you again, Derek, and I hope to see everyone again next week.